Okay, so can you guys hear me? Okay.
Yep.
Okay. So we will wait a couple more minutes. Maybe more people are coming. As a reminder, these sessions are being recorded, and hopefully they will be available in our YouTube channel soon. So if you missed any sessions, you can soon we'll be able to go back over those. But hopefully you will be able to attend these afternoon sessions, which are we would say the most important ones in this workshop, because you have access to a lot of people that experts in this field that can help you tackle any problems and also learn from the tutorials that we have available. So the way we are going to structure these sessions is, so if you, let's look at the program. Let's see. Let's go to the program. So the program is in the workshop main website. It's here on the left, here you can access the program. I sent also an email, but each day we will have 2 sessions in the afternoon. The first one is starting at 2, which is right now. And the way we are gonna work on these sessions is that the first session, at least most of the first session, is gonna be either me or other people talking through some of the tutorials. Hopefully you can follow along if you have all the programs installed and all the necessary files, so you can work around the tutorials. We are not gonna work every step of every tutorial, because that's there's a lot of tutorials in our website. So we selected a few of them. For example, today we're gonna go over the QwikMD tutorial, which Rafael explained in the morning session. And you have also some of the other tutorials that we're gonna cover in the next days. And the second session, which starts at 3:45 p.m. Central Time, is gonna be mostly office hour type of session, meaning that you can continue working on your own in whatever tutorial you want to work with, and you will have access to a group of people that will help you towards any questions that you may have on those tutorials. Okay. So basically, we are not gonna have a guided session in the second afternoon session, but we are available through Slack mostly for those questions. I suggest Slack because that's more flexible, and also anytime you can leave a question. Maybe you're finishing your work, you leave a question, and you can come back tomorrow and check that question for any answers. So that way, otherwise the Zoom chat, it's a little bit more complicated, it doesn't leave long, and people cannot respond to you once the Zoom session is finished. So in that sense, I encourage you to join Slack. If you haven't, I sent an email earlier today with a link. Basically, it's free, so you should be able to join. And in the Slack channel, there are different in the Slack workspace for the workshop. There are a few channels. There's a general channel, and the NAND and the BMD channel. So please, if you have any questions related to one of those programs, just be mindful and use the appropriate channels. That way it's easier for people to answer and follow along if you have questions. So So yes, so we have, okay, let me promote some of the TAs to panelists so people can talk if necessary without having any issues. Okay, so let's wait one more minute and then I'm gonna start. Mute Slack for a little bit. And another thing that it's, if you're new to Slack, there is an option to answer a comment or a question using a thread. Basically, it sorts everything, every message in an easier, more compact way, so you can follow along the conversations. So please use that if you're replying to any questions or asking your follow-up questions in the same thread. That way, it's a little bit more organized, the channel, and it's easier for people to contribute to your questions. Okay. Chat. Okay. Okay, let's start. So we're gonna go a little bit more in depth for talking about QwikMD. Rafael did a very good explanation about what QwikMD offers. I'm gonna try to pinpoint the most important things about QwikMD, and if you have any questions along the way, just please don't hesitate to ask. Hopefully you will be able to do this alongside, so please run BMD and open the QwikMD window. So the QwikMD window, QwikMD window is in extensions. Extension system is basically the main tab that the main part that groups all the analysis tools, all the modeling tools, all the simulation tools, and some of the visualization extras that you may say, extensions that you have. So in extension simulation, you have QwikMD. You can click that and it will open this window that Rafael already mentioned a little bit what each button works with. We are gonna go along the tutorial, which is pretty self-explanatory. So hopefully you will have a good understanding of what you can do and what you can, what QwikMD can help you with. So basically, to summarize, QwikMD is a first tool to help in the preparation of the simulations, because we've seen during this morning talks the powerful the good things that you can get from molecular dynamic simulations, and that's great, but there is some barrier to overcome at the beginning when you're a novice users. How do you set up these simulations? How you correctly calculate and simulate your system, and that also depends on the software that you're using, the MD engine that you're using. So in this case, everything that we are working with QwikMD prepares simulations for NAMD, which is the MD engine that our center develops. But in the near future, as Rafael mentioned, we are working with extending QwikMD to prepare simulations for other softwares, like for example, Amber or Chromax. Those are the main softwares for MD. The idea is that each software, each MD engine has their own tricks that you need to, their own files that you need. But usually the main idea is that you need a system file, basically the structure and the system file that defines your structure, your coordinates, and your force field, basically. So the idea is that QwikMD allows you to take care of all of that and prepares what it's called the input file or the configuration file for your simulation. So let's do that. So let's go over the first part. So this is the table of contents of the tutorial. It's quite quite detailed. We are not gonna go over everything because of time reasons, time concerns, but I think we're gonna see how far we are depending on the number of questions and the area. So like most of the tutorials in our group, we provide the example output files, meaning that you don't have to wait. Whenever you have a tutorial that asks you to run a simulation, you don't have to wait for that simulation to finish to analyze, for example, the results. All those files are available in our website. So, for example, let me go back to where I found these tutorials. So this is a website which is linked in the workshop website. And each tutorial, which is self-explanatory here, has the instructions. For example, the QwikMD tutorial has instructions in PDF and the required tutorial files. So in this case, every file that is necessary for this tutorial is here. So hopefully you already download this. So let's go back to the QwikMD tutorial, and let me move this window here. So we're gonna start from so hopefully you already installed the programs. That's one of the things that we ask you to do before coming to this workshop. So let's go back to section 5, which is to run in your first molecular dynamics simulation. So click here. I have a question. Okay, a second. It's close to you know what's going. So there might be if your laptop is a Mac and it's a newer Mac that uses one of the latest operating systems like Big Sur or is Windows. Okay. Yeah. Maybe you can check on if you have any messages in the console whenever Windows opens. There is a pop-up console that appears. If you can screenshot that, if you have any errors there, maybe we can help you with that. Yeah, we recommend to use, I mean, if you think about it, whenever you use these softwares to run any simulations, NAMD, for example, you want to have the most performance. You would like to have your simulation run the fastest you can, and usually that is you need a large supercomputer or a good computer, and that usually all those platforms run in Linux. That being said, you should be able to run this in Windows, and we have tested that in Windows, but Windows have a lot of libraries that may or may not have conflicts with some of the libraries that we use for BMD. So hopefully we can fix that. Yeah, if you can send a screenshot for the problems that you see, we can try to help you with that with installation. Okay, and they're running. Okay, so that's why also we try to do these guided sessions, because we know that sometimes people have some issues with their computers and they're not able to fix them in time. So hopefully you will be able to follow along here. And as I said, this is being recorded, so it's gonna be available next later this week, so people can go back to and check on their own. I suggest people that has running BMD was able to run BMD, just go along and try to click whatever I click. So let's read this first section, the section number 5. So the idea, I mean, I'm not gonna go over every word because it doesn't serve any purpose. But the idea is that in the first section, we are running an implicit solving simulation, which is the very first thing you can do in QwikMD. So for example, if you go to the Easy Run tab, this part here, the first part is for loading your system, okay? We haven't done that yet. And the second part here is basically what you want to do with your system, what type of simulation you want to run. So let's do the first part then. Let's run here, step 3, that says load the PDB by typing the PDB code in a blank space and clicking load. So for this part of the workshop, we are going to use ubiquitin, which is a very ubiquitous protein in the body. So this is the code is 1UBQ. So if you do that and press load, it will take a few seconds and it will load the PDB from the protein data bank database. And the idea is that since the PDB has some atom types and atom names that may or may not coincide with the charm force field, which is the force field that you use in NAMD. So you basically QwikMD take care of all this renaming of residues and atoms for you. So it just prompts a warning or an information that says, okay, I have renamed some of the atoms, some of the residues, so that it matches the force field. And these are like the histidine, for example, and the water residue to T3P, which is the one that it's using the charm force field. Okay, so once we have that, we see in the table here the contents of the PDB, which is comes from a crystallographic structure that has the protein, which is now in blue. I'm gonna switch the background using QwikMD. I can click here to white. It is a little bit, I think it's more crisper and has a best, yeah, I think it looks a little bit better, especially in the zoom. So here in the PDB, we have the protein, which is represented in this new cartoon representation, which is tells you about the secondary structure of the protein, the loops and the sheets, and the color of, you can change the color here, for example. And also it comes with, the PDB comes with crystallographic water, which is water that is there in the crystallographic process that is resolved next to the protein. And those are the oxygen atoms here in red. So once we load the system, we can continue here. But the first thing it says is that sometimes you don't want to take every component of the system that you have in the PDB. So you want to select, for example, I don't want to run the simulation with the waters that were there in the crystallographic structure. So I can do that by using this selection, and basically, which is add or remove any chain. So I can click on deselect the water, so that way I only use the structure of the protein from the PDB, okay? Because sometimes the water that is in the crystallographic structure doesn't really fill any role. Sometimes it does. Sometimes it allocates itself in a pocket that is important, so it's close to, let's say, some binding pocket, and that's really important. In this case, it's not important, so I can forgo about it, because the first simulation that we're gonna do is using implicit solvent, which is basically here is explained in detail. So what you're doing is, instead of using water molecules or solvent molecules to mimic the environment of the protein, we are going to use a continuum solvation model, which basically fits the space around the protein as with the dielectric constant, basically. So, and that's much more faster And for a first simulation, that's a good idea because it gives you a good performance for your simulation. So if you look at this here in this second part of the GUI, we can see that we have we can choose between solvent, implicit, and explicit. So let's leave it as implicit solvent, and basically let me move this a little bit. And if we look at in this part, we can open this protocol, clicking in the black arrow. And the protocol here shows that we are going to do an equilibration simulation. And if you hover here, it gives you some information about what this equilibration entails. And then we're going to run a proper MD simulation. And you can set up here, this is an easy run, so you can set up some of the parameters of the simulation. And the ones that you can set up are the temperature and the simulation time. Basically, how long are you going to, for how many steps are you going to run? Okay, so let's continue here. So it asks you to deselect what we already did, deselect the water. And then you can do, I think, what Rafael wanted to show, but he couldn't because he had an issue. This is something that is not gonna be common practice. You're not gonna do this every time, but just to show that it's available, is that you can click here on live view, and basically what it's gonna do is it's gonna run your simulation in the background using NumD and communicate with QwikMD, with BMD, and QwikMD is gonna get a hold of this information from the simulation and basically show you how the protein is moving. Basically, it's taking the trajectory files and everything that is generated and load them as soon as it jumps. I said this is not common practice because again, you're not gonna. Hopefully, you will be able to run your simulation in a computer with not paying attention. Just come back like maybe in a week, and you have your full simulation. But this is a good thing just for people that are not aware that you can see your simulation while it's occurring. Okay, so let's do that. Let's do that for the first time because so we click live view, and then it says here that we mark the live view button under the simulation setup and click prepare. So let's do prepare. So what it's gonna do is ask you for a name for the files that you're gonna create. Remember that QwikMD is gonna take care of all the files necessary for your simulation. And that means creating your system files, your taking care of your force field, your configuration file, and also it's gonna create these .QwikMD files, which are basically all the steps that you did when setting up this. It's a little bit small in the Zoom, but hopefully you will see. So let's use, for example, this is like, I don't want to name it test, but I probably will end up naming test. So let's do like one test 1 week. Okay, so you can choose your name, and it's going to create a folder. So if you select a name that is already there, it's going to prompt you and going to say you have already a folder name like this. So okay, so basically what it did is just prepare, and once it's finished, it allows you to run the simulation. So it asks you to start your simulation. So let's do that for a few seconds, of our time to show how it works. So let's click on start equilibration simulation here, which is step 6 here. And it's going to take a little bit of time. Okay, so it prompts me to ask me how many processors. So in this case, this is a not very fancy computer, so I have only 8 processors. Let's use 4 just so that it doesn't crash any other things that we're doing, like for example, the Zoom. So I can click OK, and it's going to connect it's going to connect QwikMD to NAMD. It's going to launch the MD engine NAMD in the background, and in a few seconds, a couple of less than a minute, it's gonna show how this protein is moving. And let's see. Okay. So here in the bottom, we can see the progress of the simulation, and it's going up. So it's gonna go. So this is a calibration. So we are, if we follow along the whole time, it's gonna equilibrate our simulation for 1.2 nanoseconds. Let me zoom in a little bit so you can see how the protein is moving. So now you can, hopefully you'll be able to see. So there is a little bit of movement here. Maybe we can change the representation to something that it's a little bit more, So you see how it moves. Now I'm using a different representation, and let's use this name. So you see how all these residues are moving a little bit during this equilibration, okay? And another thing you can do, which is one of the features of this live view, is that you can analyze the simulation that you're running. So if you think about it, if you've done any molecular dynamic simulation, what is happening is that you're integrating the equation of motions using the Newton motion law, and basically you're computing the force, you're using the forces, computing the forces given the interactions that you have, and then you're propagating the positions. And then every time you generate a new set of coordinates, and then you compute the forces and generate coordinates and so on and so forth. So every step you're generating information about your system, like for example, the kinetic and potential energies, temperatures, and other macroscopic variables. So let's see how we can check that. So we are still running the simulation, and we can go to the basic analysis tab here. So this is the next step. I'm jumping a little bit back and forth between the PDF and the GUI, but bear with me. So if we go to the next section, we are analyzing during the live simulation, which is what we are going to do. So it asks you to go to the basic analysis tab, click there, and for example, perform some of the analysis here. So let's try to do that. So here we have the basic analysis. As the name shows, it's a very basic battery of analysis, like for example, RMST, energies. You can click here and open different type of energies. You can do RMST with different type of selections. You can calculate temperature. So let's run this. Let's calculate the temperature. And so now it creates one plot that's labeled temperature. But if you look about it, let's open this a little bit so it fits the plot. So this plot is actually updating itself every time step, every few time step, so that we can see how, for example, in this case, we are equilibrating the system by ramping up the temperature. We're going from close to 0 to 300. So you can see that every step, or every so often steps, we are gathering this information, and we have here like the time in nanoseconds from the first time we opened this plot to now. And here we have on the y-axis the actual temperature of your system. Okay. So the idea of this is the first step is the calibration. So we want to simulate this, for example, at 300 Kelvin. So we are gonna go from low temperature to 300. So let's do another plot, for example. Let's do the RMST one. So for the RMST, we can select the already defined, for example, backbone or alpha carbon. So let's do the alpha carbon one. And I don't want to align my structure because that will mess up with this computation. But let's do this RMST and see how it changes. Basically, the RMST is the root mean square deviation from the initial structure. So basically, it tells you how how close are my new conformations to my initial conformation. Okay. Maybe someone can ask, but I can quickly go here and to delete the water molecules from the crystallographic data. We can go here to selection, and if you still have a water, it's gonna be here A and water, so you can click there and it's gonna delete it. Okay. So let's go back to the RMST. For example, here in the PDF, one of the analyses that I ask you is to calculate the RMST. It asks you to do backbone. So let's do backbone, because so that way we are doing the same thing that the tutorial asks for. So let's go to calculate, and now if you see here in the plots part, you have a new tab that has the new RMST plot. Then it's gonna also be updated every so often time step, and we can wait a little bit so it populates a few more frames. Okay, so you see it's been updated. So and we have a set of analyses, basic analysis here, energetic and thermodynamics, RMST, and then if you were to want more complicated analysis or advanced analysis, you can go to this advanced analysis tab, and we can maybe talk a little bit later on about this other analysis. But in this case, since we are dealing with a very simple protein, a very simple simulation, it doesn't make much sense to do any other analysis. Okay. Okay, so let's go back to the PDF. I'm continue running this just so that we can get a little bit more steps here. So we show how it works. Okay, we are seeing here how it increases the temperature over time. Now we are close to 80 Kelvin. Okay. Okay, so that was the first part, which was the ubiquitin in implicit solvent. Are there any questions so far? People have been following along. Any issues arise?
Yeah, I have a question. Are any of the TAs really versed in coding in Windows? Because John suggested to set the global environment variable, and I sent a link about how to do it, but I don't have a Windows, and I don't really know how to do that, but apparently that would help a lot of people with the BMD issue.
Okay, someone has any, maybe share using.
The question I was gonna ask is kind of like related. I think it's kind of related to my own field of study. So I was thinking, like, is it possible to have molecular dynamics in a vacuum? Because when I look at the QwikMD, I couldn't see any option for vacuum. And yeah, I think that is my first question. Like, can we have simulation in vacuum?
For molecular dynamics, I mean, you can definitely. For example, what you can do is you can run implicit solvent and define the dielectric constant to be 0, which is the dielectric constant of vacuum. That way, you're basically simulating your protein in an environment that doesn't do anything. Okay, your dielectric constant is 0, so it doesn't perturb your system. That's like vacuum, actually. Okay, so technically you can do it. I mean, in principle, what information would you get from that simulation? I don't know. But yes, you can do that.
Okay, just a follow-up question. So to make it more precise, so is it possible, maybe like I don't really work with like membrane lipids. I work with single lipids like PC, PG, PE, like very single. I don't work with membrane lipids. So is it possible whereby I can simulate maybe one of those, maybe the cation of a particular single lipids in nitrogen, but the nitrogen has a particular density and everything is all in vacuum. Is it possible using QMD?
So when you're saying QMD, you're asking for more regular classical molecular dynamics or quantum mechanical molecular.
Like both, if I can use both, but maybe like Q, because I think is it QMM, something like that, but I'm not really sure because I'm not very good at MD. I'm just a beginner, so I
okay. Yeah. So the main difference between classical and quantum is the way you treat your molecules. Okay. So basically, it's how approximated you're trying to treat your molecules, your atoms, and your electrons, basically. So we are in this workshop, we are mainly focused on classical molecular dynamics because we are interested in solving problems for large, typical hundreds, thousand atoms. Okay, so we usually have a protein like this one, for example, it says there 1,200 atoms. So that is a size of system that is pretty much untractable. You cannot do that with quantum. Basically, the approximation that you would take to solve this in a quantum mechanical calculation, it will take you years to solve. So that's basically not possible. Now, if you're trying to solve a problem of a single lipid, let's say PC, for example, and maybe the counter ions, you could do that in quantum, but again, it also the most important thing that you need to think when you're trying to decide whether I do classical or quantum is not only the size of your system, but also the question that you're trying to answer, okay? Because there are some questions that cannot be answered with classical molecular dynamics, okay? So basically, and also there are some questions that are not, you don't need to go to any more efforts, and you don't need to go to any more higher approximations to solve those questions. Okay, so it's a little bit of in principle you can do anything with anything. Okay, you can use any method in any system, but the problem is how long it takes to solve that problem. Okay, so without going into any specific information about your system, I cannot really answer that question. But in principle, the answer is yes, you can do that. Whether you get enough data in a reasonable amount of time, like I don't want to spend like 10 years to get my results. That's another issue. So, but I would say that if you're interested in a lipid, and maybe the interaction of the lipid with some other species, then probably you can use classical molecular dynamics for a good first approximation. And the other part of your question was using nitrogen as your environment.
Exactly.
Yeah, so I'm not experienced with using that type of environment, but I would say that I would argue that nitrogen is pretty inert, so it's probably like doing vacuum, right? So you wouldn't expect any interaction between within nitrogen. Yeah, so I would say that you can do that. I guess I know people in our group have experience simulating explicit gases like nitrogen and oxygen. So I would say, but always in solution, I think. So it's like the medium is water and you have some of these gases permeating through the membrane, for example. But I would say that the interactions that you would expect are pretty negligible. So you will probably be fine running in vacuum, I would say.
Okay.
Okay. So any other questions?
No.
I have a question.
Yeah.
So first we gave the simulation time to be 10 nanoseconds, but at the bottom, just at the side of progress, there is another simulation time, 1.2 nanoseconds.
That's because we are running. Let's go back to here. So we are running the calibration, okay? And this is actually the simulation time for the whole thing, the calibration and production what is called the production simulation. Usually, when you run this in your work, you prepare your system and equilibrate it first for a few nanoseconds, maybe 100 nanoseconds, depending on your system. And you usually don't use that information, that results from the equilibration, as your data for analysis. You start from there and run a much longer production simulation. So that is the production. The 10 nanoseconds is actually the time that you will run your production simulation. So actually, so let's finish this, or let's pause this, because it's gonna take probably the rest of the day. This is as I said, this is not the a feature that you need to use every time you run the simulation, just so that you know that you can do that, but eventually you will run in the background, or like in your computer, and come back a few days later with your results. So let's finish this. Clicking finished, and you see now it came to a stop, and now it says, okay, start production. So production is basically the MD part of your protocol, okay? And that will take like 10 nanoseconds or whatever you put that in that entry, okay? Yeah, Sonal?
Yes, so I was able to run the simulation, but when I was trying to plot the temperature, I was getting an error that said something like cannot use geometry manager grid inside. And it happened the same thing when I tried plotting RMSD or anything from the energies subsection.
Okay. What platform are you running? What operating system? Windows, Linux?
Yeah, it's Windows 10.
Okay.
It might be the resolution is small and I have like too many windows open, I guess.
Okay. Yeah, if you can screenshot the error and post that as a message in the Slack channel, so people can try to help you with that.
Okay, yeah, I already did that. I was just wondering if you have any quick ideas.
Yeah, no, some of the errors are known, and some of the errors are like popping up every other day because people are like have different versions of Windows. Sometimes the libraries that are there are not compatible. But yeah, hopefully people can help you with that. Okay.
Okay, thank you.
Okay, so go ahead, Sam.
Yes, yeah. Actually, I'm running on 2 processors.
I can barely hear you. Can you try to?
Hello, now it's okay?
Let me go and increase my volume, please. Be mindful. Okay, go ahead.
Okay, 1 minute, please.
I can hear you now.
Okay, so the question is that I'm running the MD simulation on WSL, that is window-based Linux. And when it's running, then the MD GUI gets struck as it is completed, and the process will be allow me to use the VMD GUI interface. So the question is that when I use in some clusters, so some clusters don't have the X servers, so I'm not able to use this as by clicking it. So is there any way to giving the commands and something like that?
Yeah.
So
yeah.
directly use.
So we can look at that. Let me go one more section, and then we can go back to your question. Okay.
Okay. Thank you very much.
Yeah. Yeah, Pete, you have any questions?
I think I'll just my question pertains to using QwikMD and using the input files for a HPC or supercomputer, but maybe we can tackle that next.
Yeah, that's exactly what the other participant was asking. So the idea is that yes, we are showing here in this demonstration how you can run basically your simulation in your laptop or in your workstation, but as I said at the beginning, that's not the best way. The best way to use your resources. You should probably once you are sure your system is equilibrated and everything, you should use the files that are prepared in QwikMD to run this in your HPC supercomputer center. So that's the next step. I'm gonna show you how to do that. Actually, QwikMD prepares a few folders, but I don't want to skip ahead, and I want to finish with this part first, and then we can see what are the files that are QwikMD prepared. Okay, so let's. So I already stopped this. And I don't want to run my production simulation right now. So I want to skip this and go back to the tutorial. Okay, so what I'm gonna do is I'm gonna click here, reset, on the bottom right part of QwikMD, and what it basically does is just, as I said, resets everything. So it goes back as if I just close PMD, and so now I can load a new molecule or the same molecule and do another simulation. So let's do that. So now I want to do. So the first simulation that we did was implicit solvent, and I said this is it gives you some insight of your system. It's pretty fast, but it's usually not very. It's not the best you can do. I mean, the best you can do is actually, if you have the computing power, you can run these simulations with explicit solvent. So let's do that. So let's use. So let's follow this part of the tutorial, which actually asks you to run again ubiquitin. So let's do that. Let's load again this simulation, this system, sorry. So now we have again this part here. So now I'm gonna leave the water molecules there, because actually we are gonna solvate the system. Basically, we are gonna include more explicit water molecules. So I don't really care about the waters that were there. And at the same time, it's gonna be good for demonstration purposes. Just bear with me. So I'm gonna leave the water now there, and what I'm gonna do is I'm gonna go here to solvent, and I'm gonna change that to explicit. Okay. So basically now it allows me to choose the salt that I want to use. So I can choose any salt to. This is basically to balance the charge of the system, because sometimes the protein is charged, has some charge residues. So I can balance and neutralize the system. Otherwise, if the system is not neutralized, it's going to give you errors in the simulation. Okay. So we are here creating a salt solution. This is the default concentration of salt, which is close to the normal salt concentration in the body, I think. And sometimes you want to change this because you're interested in the effect of the salt in your simulation. So that's one thing you can change. Okay, so let me. Okay, it asks you to also click live view. Okay, let's do that. Let's do live view, and let me change this to shorter simulation so it doesn't take a long time. So I'm gonna run only for 0.1 nanoseconds. So I'm gonna go to prepare, and I'm gonna do, I call it test ubiquitin water box. So it takes a while, a little bit, hopefully it doesn't crash. And while we wait, okay. So now something that I wanted to show is that now, if you remember, when I load this protein, that protein from the ubiquitin from the protein data bank, it came with only the oxygen atoms. Because basically, when you have a crystallographic structure, you cannot resolve the hydrogen. So basically, you're given information about the heavy atoms, what you call the carbon, oxygen, nitrogen, and so on. So basically, now if we run the simulation with only these crystallographic waters showing only oxygen, that would of course be wrong. You're not having water actually. So what I wanted to show here is that we populate all these oxygen atoms with hydrogens, and now we have actually water here. And the same was done for all these protein atoms, that were all the residues in the protein. Okay. So let's start the calibration simulation. I want to run it just a little bit let's do that. Let's do again 4 processors, and hopefully it works. And another thing is that now we can see that QwikMD shows you the water box, the size of the box with these yellow lines. And once it starts running, I can show you how the protein is going to move around the cell. Okay, it starts running, I think. Okay, while we wait, let's go over the PDF. So yeah, okay, so it tells you that, again, explicit solving is a much more computationally demanding task than the implicit solving, because now we have more atoms in our system. Remember I said before that the protein ubiquitin had 1,200 atoms. So now if you look here in the PMD main window, now we have 40,000 atoms. Basically all those extra atoms are water molecules that I added to mimic the environment, basically, of the protein. And also I have water, and I have also salt. I have sodium and chlorine ions. Okay, so now it started, and if we zoom in, you can see that it moves. Okay, what I'm gonna do is I'm gonna finish this, and I'm gonna load and I'm gonna go back and look at the files that it generated, okay? And to answer the questions about this. So I'm gonna finish this, okay? Okay. So it asked for me to, okay, I'm gonna reset this. And let's see the files that it generated. So I'm gonna open the terminal. This is a Linux machine. So I'm gonna go here. Okay. Let me increase the font a little bit so that people can understand. Okay. So the most recent simulation that I prepared is called it was called test-1ubq-waterbox, and it created here a QwikMD file, and it created this folder. So let's look at the QwikMD file to see what it contains. Okay, so I'm gonna use the VI, which is the text editor that I use typically. Okay, so let me open this a little bit more and see what it is. So this is not necessary. You don't need to go over this file, but I would like to spend like 30 seconds going as an overview of what you have here in this file. So basically, there are a few commands that were used by QwikMD, so that the next time you open QwikMD and load this file, you have exactly the same setup and exactly the same everything that you did before, you can reproduce exactly. Okay, so for example, this is in a programming language called TCL. You don't need to know about that, but basically you can understand probably that what it's doing here is setting up this variable to 1. Okay, that's only one. I don't want to go over any details, but basically, again, everything that you did up to when you click prepare, and prepare meant prepare this simulation, this is here. So now let's go to the folder that was prepared here, and let me list. And here we have, let me go back to the PDF if I can. Yeah. So here we have, two files, two folders, sorry. One is called run and one is called setup. So if you go over this tutorial, now there is a section that is called running your simulation outside of QwikMD, which is what people were asking for. And what it tells you is that actually you can do that. And what you need to do is navigate to the run folder, which has all the files and everything that you need. So let's do that. Let's navigate to the run folder. So let's go to cd run, and let's list whatever it is here. So there is a series of files that basically, there are some PRM files, which are parameters for the force field. There are some QwikMD files, and these are the configuration files that you need to run your simulation. Okay, so for example, here it says that you can run this by copying this the syntax of this command. So what it does is basically calls the NumD command if you have it installed. I have it installed. So, and you can do +p with the number of CPUs. So I was using 4 before, so let's use 4 again. And now we're gonna run this file, which is the calibration configuration file. Okay, so if I do this, it's gonna run the simulation in the console. Okay, so let's do that just for a few seconds. Okay, so it's running. Okay, interacting and the awaiting connection. Okay. Let's go back. Okay. Because I prepared this simulation with the live session, it's asking me to connect to some live session of QwikMD. So that's not an issue. So let's list again. Okay, so let's go. How much time we have? Okay. So how would you do this in your high performance computing center, your supercomputing center? So basically, what you do is you will prepare your simulation with QwikMD either on your laptop or on your workstation, and then you will copy this run folder. Okay, all the files into your HPC cluster, and then you will call your using the scripts that are given by the HPC, calling NumD with this file, with for example the calibration file or the production file. Okay, and that would be the idea. And that's why we think QwikMD is very powerful, because you can bypass one of the most challenging parts, which is preparing the simulation. Okay. Any questions so far? Okay.
Hello.
Yeah.
Yeah. Just a short question. One in the calibration step, does this already include the minimization and heating parts? So after finishing the equilibration part, we could just proceed with the production step.
Yeah. So usually the minimization comes first, then the calibration, and then the MD. So let's go look at this configuration file that actually did the equilibration, see what it did. So, okay, let me show what I did. So I just used BI to open this configuration file. Okay. And let's see what it has. So I think Rafael mentioned that usually you have this structure of this of the configuration file asking you for the PDB and the PSF, the temperature. You may have harmonic constraints, parameters of different kinds, periodic boundary conditions if you're using a water box, for example. Thermostat parameters, biostat. This is something that you may or may not want to change, but in principle, it's for the basic simulations you don't need to change. The time step, and so on and so forth. The Forcefield Parameters part. So let's go back here. So at the end. So it says here there is this line that it says minimize 1000. So what it does is actually is this simulation that we did that we call equilibration actually did a minimization first. So the first thing we did was a minimization of 1,000 steps, okay? And then this part may be a little bit complicated, but basically what it does is just ramp up the temperature. Remember, I show you how the temperature went up from, in this case, it goes from, this is a loop that basically resets the temperature increasingly. So it goes from 60 first to, here is the increasing temperature part of the for loop, and to the temperature, which is, I show at the beginning that was 300, okay? So this is like a ramp of temperature. And then it ran 500,000 steps of equilibration properly, okay? Does that make sense?
Yes. Thank you.
Okay. Okay, let's go back to this. And so let me go back to BMD and the QwikMD part. And so what I said about these QwikMD files, so let's say I already finished with my simulation, okay? So I did my simulation, it finished in my cluster, in my HPC supercomputer, or in my laptop, or whatever I did. So I can load this simulation and analyze the results, and let's do that. So I'm gonna reset again. I don't remember if I reset it or not, but let's do that. And now instead of loading my molecule again, as I did many times, what I'm gonna do is I'm gonna load here a file that already finished my simulation. So I'm gonna use, I downloaded here the tutorial files for QwikMD, and I'm gonna go over those files. For example, there is a folder that is called Ubiquitin here. So I'll go there, and I click here in ubiquitin.quickmd. So if I load this file, remember I said that this file contained all the commands that all the parameters and everything that I did in the GUI, in the interface. Now I'm gonna get also the results of the simulation. So I load this, and here it prompts me to select what type of simulation results I want, okay? Because remember, I run equilibration, production, okay? So let's load everything. So let's load, or let's load only the production, let's say. And I want every step. I want to have every step because those are like not that many steps. Okay, so now I'm gonna, again, this is like once I finish my simulation, I can load these results and I analyze them. Again, so basically, if you were running outside of QwikMD, which is the recommended way, you can go to your supercomputer. Once it's finished, copy everything back to your system. Okay. Sometimes the files are quite large, but basically you can copy them to your system, to your computer. Load this into QwikMD, and now we can analyze the results again. Okay. So now we can go to, for example, this is only 251 frames. But we can show how it looks. This is a simulation. And now it makes sense to show why I kept the crystallographic waters here, because those are the ones that are already labeled and already shown. And you can see here that initially they are like close to the protein, because that's where the X-ray crystallographic data show the waters. But after a while in my simulation, they just move around and appear anywhere. Okay. Okay, so let's do some analysis. So for example, I can run, this is the production simulation. Okay, so let me run an RMSD for the backbone, and I can do that. Let's say calculate, okay? And if you're familiar with RMSD, or if you trust me, the RMSD tells you how similar the structure every time step, or every so often time step, is, how similar it is compared to the reference point, which in this case is the initial structure. Okay, so basically what I'm doing is I'm comparing, I'm giving it the value to each frame compared in comparison with the first step. So the first step, remember, was the crystallographic structure. Okay? So I don't necessarily expect to be everything to be similar to the crystallographic structure, which was the initial one. Okay, so you can see here that the values of RMST quickly go off from 0. 0 is like perfect matching. There is no difference between my structure and the initial structure or reference structure. So it goes up, and then it goes to almost 20. But the thing is that this is an RMST which is not technically correct, because I haven't aligned my simulation, my protein. Because if you look at it, the simulation from the first step, you can see that my protein just moves around in the water box. Okay, and what I'm doing with this RMST calculation is basically comparing the position of each step, irrespective of the translation of my protein. Okay, and that's not very good. What I want to do is I want to calculate a second or a different RMST plot where I align my structure from in each step. Okay, so if I do that and I calculate again the RMST, what I have is now I can show you how it aligns. So align all the frames. So now all the frames are like in the same reference point, and what it changed is basically the rest of the system. And now the values of RMST are relatively small, close to 1 or 2, okay? Compared to, okay, the other plot went away, compared to almost 20. But just that 20 was a fictitious RMST because it just translated the protein along the box, okay? So the RMSD is one of the first analysis that you do because it tells you whether your system is or your simulation is behaving normally or not. Because if you think about it, the RMSD tells you how different your structures are one another. So if your RMSD is going back and forth, crazy numbers, your simulation is behaving very erratically because it's just changing your system all over the place. Whereas if you see kind of like a plateau or a constant RMSD along the time, you're pretty much confident that your simulation is stable, let's say, okay? So that is one of the first analyses that you need to do to confirm that the results of your simulation are okay, are trustable. Otherwise, if your RMSD gives you like crazy fluctuations, then anything that you do without simulation doesn't hold any value, okay? So, and here you can see that this is a very, I simulated for 5 nanoseconds, and the RMSD goes from 0, which is the reference from my crystallographic structure, to 2, that goes back, and then kind of like stays around constant around 1.5, 1.5. In any case, I would suggest you run your simulation for a little bit longer, like, I don't know, at least hundreds of nanoseconds, and check the RMSD is okay, okay? Unless you are actually using some non-equilibrium simulations, when then your RMSD will fluctuate because you're deforming your system on purpose. If you're running equilibrium simulations, you will expect that your RMSD will stay constant, okay? Unless, of course, your system is experiencing some radical conformational change that you like to see, then okay, your system is moving away from your structure, from your initial structure, and then you're like opening a pore or opening a channel or something like that, then your RMSD will change. But if your system is just like behaving normally in your solution, you will expect that the RMSD will be constant, okay? Okay, so let me stop here for a second. Any questions so far?
Excuse me, can you hear me?
Yeah.
Okay, good. Is it true for every system that RMSD should be flat at some point? Like after, I don't know, a few nanoseconds, it should be totally fluctuating over something?
As I said, I would say yes, except in cases where you experience some radical conformational changes, okay? Which is sometimes happens. I mean, your protein has some different conformational positions. For example, if you heard about this coronavirus simulations where they simulated the spike protein to see how it behaves in different conditions, and you will see that the spike protein is kind of like a it has like a part of the system that basically opens up every so often. Okay, and that is something that they saw, people saw in the simulations without having to, I believe, without having to do any non-equilibrium. So of course, if you compare the RMSD of the closed state or closed conformation of your spike protein, it's gonna be pretty much oscillating around the value. But once you've changed the conformation and like in your new state, then it's gonna change. Your RMSD is gonna change, and you're gonna see that, and that's also a powerful some of the features that RMSD gives you. This is a pretty simple analysis. I would say it's one of the simplest one you can do, and it gives you some information. So you will expect to see a plateau in your RMSD if your structure is stable. That's a good indication that you have a stable structure, and then you will see some changes in that RMSD if you see some conformational changes in your system. Okay.
Okay, perfect. But sometime in my simulation, I have few proteins or few backbones, and I can see that it's not going to be flat around maybe after 50 nanosecond or even 100 nanosecond. Is it normal? Is it natural to have?
Yes, the RMSD is a mathematical function that depends on the number of basically of the selection of your RMSD. If you think about it, here you can do an RMSD comparing any selection that you want. So I can, in this case, I'm using the backbone, basically all the heavy atoms of my protein, but I can also use the alpha carbons, and I can use, for example, no hydrogens, and I can use all the atoms. So basically, what you're saying is that if you have a peptide that is small, then any changes in that peptide is gonna affect the RMSD because you have a few atoms to compare the differences, and every single atom is gonna weight heavier in your computation, okay, in your RMSD calculation. So if you have a small protein, then RMSD values are gonna fluctuate more usually, okay? But if you have a relatively medium-sized protein, RMSD should be, especially some kind of like globular or spherical protein like the ubiquitin, which is like it's not gonna fluctuate much more, okay? If you have a protein that has like a completely different structure, like I don't know, more like longitudinal structure, then maybe yes, that any change, let's say if you have a protein that is like this, any of these movements that can be normal in your simulation, that will change the RMSD. Okay, so RMSD is a good tool, but it's not perfect. It's gonna give you you need to analyze your system, and that's the most challenging part. I mean, you always need to know your system and know how to take the best from every single analysis that you can use. Okay.
Okay, thank you.
Okay, so we have a couple more minutes, 15 more minutes. Let's see if there is any questions. Okay, some people may already have go over this. So let's go back to here and let's reset this. So let's go back to the tutorial. So the next part of the tutorial, as I said, we are not gonna tackle everything because it's, but I would suggest you to maybe work on your own if you're interested during the next session, which is gonna start after the break. And again, if you have any questions, we can discuss them through Slack. So in this following sections, there are a few real case studies that you can do that involve a little bit of a more complex setup for your simulation. Basically, imagine that in the first one you have a mutation in a protein. So basically, it tells you how to mutate a residue using QwikMD. If you think about it, I downloaded the protein from the protein data bank, and maybe there is no mutation, there is no PDB, or there is no structure for the mutation of that protein. Okay, so I want to mutate it artificially, let's say. So you can do that with QwikMD, and this is how to do that. It explains how to do that. So let me show you how. In the few more minutes that we have, let's go over how to do that. So it asks first, it tells you, okay, let's load the wild type simulation. So basically the natural occurrence of this protein. And this is the code 1Q array. So let's do that, 1Q array. So we load that, and this is okay, prompt me some information about this protein. Okay. So now this protein has a little bit more, a few more components. Okay. Okay, let's do this. And what it tells you here is that something that I'm gonna talk a little bit more on Wednesday when I talk about how to tackle problems regarding force field. If you think about it, sometimes you want to do science on things that have not been studied yet. Okay, otherwise you're just repeating simulations that were performed before. So if you want to do that, at some point you will encounter that the system or part of your system, some molecules in your system, are not present or have not been parameterized in your force field, or are not suited for your force field. So when that happens, and I'm gonna delve into this on Wednesday, you can basically create or fit the parameters for your force field using some advanced methods. Okay, but whenever you have that, and sometimes it's a little bit difficult to tell. If you run your simulation and you don't have the parameters for your molecules, any MD engine is gonna tell you, no, I cannot run this because I have parameters missing. So in that case, QwikMD gives you some information about what parts of your system are missing in the force field and how to deal with that. Okay, so if you go here to structure manipulation, you're gonna open this new window that is basically like some explanation about, okay, be careful because some of the parts of your system are not in the force field. Okay, and you cannot simulate this until you deal with this. So if you look at this here in the bottom right corner, there is structure check, and there are some warnings in yellow that some of the torsion angles are kind of like weird, but you don't need to take care of that yet. The most important problem, the most pressing problem, is that there are some parameters, the force field, that are not present. Okay, so let's go scroll over here. And okay, so what is happening here is that there is a residue that is called GTP that is classified as nucleic, that is not recognized in the force field. And this is kind of like a trivial case because GTP is usually simulated. So let's see what the tutorial asks us to do. Okay, we're trying to solve the problem of having one part of my system that is not in the force field. Okay. So okay, so let's see. Was it jumping up? Okay. Let me hide the water. And the water. Okay. And this is the part that is missing. It's kind of like showing here in this licorice representation. This is the one of the species that is like a coin change of energy in the system. GDP is present in the respiratory system. And if you go to here to structure manipulation, it shows you here that GTP is not recognized, is unrecognized residue. So what we need to do is basically add this information of the force field regarding this GTP into the QwikMD basically directory or collection of force field parameters. And we can do that by here clicking in add topo param. So we can do that, and it prompts us to add extra things here. So we can do that. In my case, since I already use QwikMD for other things, I have a list of things that I added. Here are the things that I added, but you probably don't have anything, or at least don't have as many things I have. So what you can do is to add this, you can click here in the plus and search for the file that you created or someone else created for you. Okay, so let's do that. So let's go to, I need to go to my home directory. I have a tutorial folder, and here is QwikMD tutorial files. So the idea is that someone, you in the near future, or someone else, prepare the parameters for this molecule for the force field. Okay, and now what you're doing is, okay, you're taking that file and using it here in QwikMD. Okay, bear with me and wait until Wednesday. And Wednesday, I'm gonna tell you how to do that, how to extend the force field for other molecules. Okay, so we can go here to this is the RAS, and here this is the topology and parameter file, which is an str file that contains some of the nucleic acids, including GDP and GTP. Okay, so I do open, and now I have here series of things. Here I want to add the GTP here, nucleic, and I want to do apply. Once I do apply, it's gonna say, do you want to add? It's gonna be added to the library. Do you want to continue? Yes. And it says, okay, I added this topology and parameter file. So now the next time you use this, it's gonna be recognized. So let's do that. Let's close. It asks you to reload QwikMD just so that it doesn't fail. So let's reset QwikMD and go back to what was the name of this PDB, 1Q array. So now I'm loading this. Yes. And now if I go to structure manipulation, so now it didn't give me an error. Okay, so now if I go to structure manipulation, everything checks. Okay, there is no part of my system that doesn't have the appropriate parameter files for the force field. So basically, I am good to go to run my simulation. Okay, that means that I only need to do this once, and from now on, every time I run a simulation with GTP or GDP, sorry, it's going to be present in the library of topology and parameters for this. Okay, that's the idea. Okay, so what else? Okay, so the next thing is to run the simulation the same way we did with ubiquity in the first couple of sections. So now the next thing we're gonna do, we have 8 more minutes to run the mutation, to do the mutation. So now I wanna do a mutation. So if I go here to structure manipulation, you can see here that one of the options here is mutate here. So step 7 says go to RAS wild type simulation and go to structure manipulation here and select mutate in the table and click glycine with the residue 12 and choose value. Okay, so basically to do this artificial mutation, you can select glycine and click mutate and change here where it says glycine. It prompts me to select any other residue for the protein. So I can choose, for example, valine, and it says here, okay, I'm mutating glycine to valine. Okay. Sorry if I butcher the names of the residues. And that's it. That's the simple thing. If you want to run a mutation simulation, if someone already did this without QwikMD, you can, you know how difficult this is, or how complicated, or how many steps you need to do. This is like very simple, very straightforward way to run a typical production simulation. Okay. So the next thing will be, okay, I'm gonna run any checks. That's fine. And the next time I click prepare, it's gonna prepare my simulation with this mutation, specific mutation that I did. Okay. And that's it. Okay. So that will be, okay. So the next part of this section is ask you to compare the simulations, the wild type, which was the original one, and the mutation. And you can do that maybe in the next session in the afternoon. Okay. Okay. Any questions so far?
Hello. Yeah, just a short clarification. So say for example, we did our simulation run in a computer and we were able to generate trajectory files. Those trajectory files are the .dcd files, right? So is that the file that are gonna use for QwikMD for doing the analysis? So that's the first question. So the second question is, I just would like to ask, what's the some clarification on the other files that were produced, like the .vel, the .xst, xsc files, etc.
Yeah. So I think that if you want to use QwikMD for the analysis, you should gather all the files, all the folder that says run, all the files, you copy them. Yes, the trajectory file is I would say, one of the most important files, because it tells you actually the coordinates of each frame, or each frame that you recorded. But for QwikMD, what you need actually is the .QwikMD file. That file is the one that is gonna know the structure of all the files that are in the folder, in the run folder, and it's gonna load the trajectory file. So yes. What other files are in the run file? So let's go to check here in the console, in the terminal. So let me go to, instead of my folder, the tutorial folder that has so let's go to RAS. There's no files in RAS. Okay. Let's go to the ubiquitin folder. So this is the folder that has the files for ubiquitin in the tutorial. Okay. So there is a run here. So if you go to the run folder, this is the file. These are the files that are in the run. So here we have the example files. We have the calibration files, which is the step 0, and the production files, which are step 1. So what is the meaning of each of these files is something that is going to be important for you to know, but basically I want to give like an overview. So I already mentioned the configuration file, which is the instructions that you give to NAMD to run. The log file is basically all the information that came from the simulation. So basically, for each time step that I run, what are the temperatures, energies, and everything. All the details of the simulation are in the log file, so that's also important. The DCD file is a binary file. I cannot see what is in there. It's a binary file that is basically compressed so that it has all the coordinates of the trajectory. So that's also important. What else? These files, the core file is a coordinate file usually for the last step, or for the step that you're running currently. The same for the XSC and the vel file. So these are files that are being updated every so often, that contains the current information, in this case, the velocity of all the atoms. The XSC is the information about the cell that you're running, so the information of the cell. So if for example, if you're running a simulation that has, if you're running a constant volume simulation, then your cell doesn't change in size. But if you're running a constant pressure simulation, then your cell is gonna fluctuate, and that fluctuation is present in the XSC file. But basically, usually what you get is not this file, but the one is labeled restart.xsc, because that is the one that you probably gonna use to restart your next simulation. Let's say you wanna run for 200 nanoseconds, but you only run for 100, and then you finish, then you use that restart file so that it knows all the details for your simulation. Yeah. Okay.
Thank you.
Okay. So we are on time for the break. If are there any pressing questions about what we went over this time?
Can I just make a comment?
Yeah.
Sorry, John has joined our Slack channel, so he's probably the best one to be able to help with the errors if you're not getting QwikMD or VMD to work. So if you're still having issues, can you please just take your screenshot and post it in the general channel, and then hopefully he might be able to help you get it going, and that way you'll have it for the second half.